All right, so there are some questions regarding gravitational field. Okay, I think I also want to remind you that when you do past year questions, you should prioritize the later ones. So try to prioritize first 2000. So this is the order that you should prioritize doing questions, right? So you should prioritize the 2020s to the 2023. Okay, this is the minimum entry. You should at least do this. Okay, if you find yourself a little bit more time, then do 2018, 2019. Okay, if let's say you still have more time, you work backwards. So 2016 to 2018. All right. Well, the reason being is here, this year is when the grade threshold is the highest. So meaning when Cambridge feels that the questions are too difficult, they reset the formatting or the way they ask questions, because they will be thinking, hey, students have a good sense of how we are asking questions. So we want to change the way we ask questions just to make sure that the students are not, showing that they can do physics by memory or pattern recognition. They want to see whether you can do physics because you really understand the physics, not because you recognize the pattern. So they tend to change things up every year also, depending on the students' results. So I would recommend, doing them in this kind of era. Like Taylor Swift had different era for era one. Okay. So anything before 2016, especially before 2012, you only do it if you have already done everything else and you don't know what to do with yourself and you're too bored, you got no other priorities, then sure. Okay, but don't do questions from 2003, questions that are probably older than you, but then you forget to do the 2020 or the 2021. That one is no good. Okay, so try to do the recent one, and then only when you finish the recent one, you got nothing to do with yourself, then if you still want to do the 2003, you can go ahead lah. All right, so this question is from 20, so hopefully that's clear. You plan your life accordingly, which means when I suggest questions, I tend to start, I don't go, very seldom I go earlier than 2016. If I go earlier than 2016, which by the way is 7 years ago, it's because the question is either important to show certain understanding, important physics theory, or because there are certain patterns that I want to highlight to you. All right. So just a heads up, if you are doing old questions, I hope you are not taking away the priority from the recent questions. All right. Anyway, that being said, we can always learn something from a question. So we're going to jump straight to part C, because part A and B are common definitions and explanation. Okay. And also, because this is very old, do not rely on the mark scheme for answers. Okay. Especially this kind of explain or define answers. You know what? Let me look at the mark scheme so I can comment. So sometimes as time passes and they feel like students are getting better, they will also tighten the mark scheme a bit, meaning they will make the question, make the mark scheme a bit more stringent. Why they do that? Well, it's because this May, June 03. It's because they would like to make sure that students know what they're doing. Okay, anyway. Well, this one, the old definition in the mark scheme, it says work done in bringing a unit mass. So this one is generally not accepted anymore. We want a definition where it is work done per unit mass. Okay, so you can do the question, but make sure you update the mark scheme to the most recent years, 2020 onwards. Meaning you go and look at the 2020 question with a similar definition and then see what the examiner report requires from you. Even I have to update my notes sometimes. Okay, so it's work done per unit mass in bringing it from infinity to a point. So work done per unit mass when bringing it from infinity to a point in the gravitational field. All right. So this part here, moving unit mass, is not that accurate anymore. 1 mark may be deducted. Okay. So it's the recent updated mark scheme. All right. Explain why the GPE near to an isolated mass is all negative. This one is also in your notes, but if you look at the mark scheme, this work got out is a very problematic statement. Work got out means work go where? Okay, so if you look at the recent mark scheme, they have already stopped using this problematic phrasing. Okay, but we don't use this anymore. What we would write is the first statement is still okay. The gravitational potential at infinity is defined as 0. Okay. Number 2, we prefer to not talk about forces anymore. This is still not that bad. It's an orange card, so meaning you'll probably still get marks. Okay, but we prefer if you say gravitational fields are always attractive. All right, this is the second point. Okay, so hence, work is done by the gravitational field to bring the mass. Work is done by gravitational field to move the mass from infinity to a point. In gravitational field. So GPE decreases and is always negative. Okay, so work got out is no longer an acceptable phrasing, especially in 2023. This question is 20 years old. Okay, so just a heads up, if you are doing old question, here's an example of how you cannot rely on the mark scheme to answer explanation and definition question. Please update yourself by looking at the recent questions and adjust the sentences accordingly, like what I'm doing now. Okay. All right. Thankfully, calculation is still calculation. So it says here the Earth may be assumed to be an isolated sphere of radius this much and the mass this much concentrated at the center. An object is projected vertically from the surface of the Earth so that it reaches an altitude of this much. So I'll draw that for you. So this is my Earth, okay? And this is the center of the Earth. I know the radius of the Earth, 6.4 times 10 to the power of 3 km. It says that I'm going to throw an object vertically from the surface of the Earth. So my object was here, and I'm going to yoink it upwards, okay, so that it reaches an altitude of 1.3 times 10 to the power of 4. So this 1.3 times 10 to the power of 4 is measured from the surface of the Earth. Okay. Altitude means height. Height from the surface. So here to here is your 1.3 times 10 to the power of 4 km. So step 1, I'm going to mark my initial position and my final position. Okay. So they want us to find the change in gravitational potential. First things first, I write down the equation for gravitational potential, negative gm over distance r. Okay. So this would be the potential at the final position minus the potential at the initial position. Potential at final position is negative gm over r final position minus negative gm over r initial position. Okay, first things first, I'm going to factorize the equation. So a common mistake that students do is that, like this point, they immediately substitute, and then they'll make a mistake because they are not careful in their substitution. So the first thing I want to point out is that I'm going to take out my GM, general manager. Okay, and what I have left is negative 1 over RF plus 1 over initial distance. Okay, again, from the diagram, it should be very clear that here to here is your initial distance, and then here to here, the whole thing here is your final distance. Okay, then I can substitute my values in. So 6.67 times 10 to the power of negative 11, 6.0 times 10 to the power of 24, big bracket. This is 1 over, I'm going to take the radius, initial radius Ri. So that will be 6.4 times 10 to the power of 3. This km needs to be converted. Okay, so that means times 10 to the power of 3. Okay, this is Ri minus 1 over Rf. So what is my Rf? My Rf would be the whole thing. So I need to add them together. Okay, so I will have 1.3. This 1.3, I'll rearrange a bit, 13 times 10 to the power of 3, okay? So that I can settle the prefixes and throw them outside. So move this here a bit. So this one would be 1.13 plus 6.4. And then the whole thing times 10 to the power of 3. And then times 10 to the power of 3 again for km. Okay? So I only substitute later when I think the equation is ready. All right? So based on your working, I'm not quite sure what you are subtracting. Like, I don't really understand your working. Okay, because whatever I have here, so let me continue this. This one would be 6.67 times, maybe I'll just press my calculator. I'm a bit struggling to understand the subtraction here. Okay. So when you subtract like that, it's not the same, because what I'm doing is I'm doing this. This GM is a constant. So let's say this is K. I'm taking negative K over A plus K over B. So I can take out my K, then it will be 1 over B minus 1 over A. It is not the same as K over B minus A. Okay? Because it looks like what you are doing. This entire thing is your K, and this is B minus A. Or A minus B, because your negative is here. Okay, so we never subtract the distances outside of the equation. It don't work that way. All right. Let me know if that makes sense. Well, what have I done? Okay, so it is not the same. It's negative. This is not the same. Okay, so then you just press your calculator. Press your calculator, it's just 1 mark, and you should be able to get the answer. So I'm not going to spend too much time here. All right, so this is basically the comment I want to make about doing all questions. And also, if I continue this, it is, never mind, I'll check. 6.67, negative 11, negative 24. I tend to put the 10 to the power of 6 outside. So what I have here is 4.00 times 10 to the power of 8. And then 1 over 6.4 minus 1 over 13 plus 6.4. So this would give me 4.19 times 10 to the power of 7 joule per kg. All right. So just a heads up, whenever you do this calculation, take out the constant and then handle them step by step. This one you need practice on. Okay. Don't subtract the distances inside the equation. You are taking the potential at one point, subtracting with the potential at another point. All right. And then it says here the speed of projection from the Earth's surface, assuming that the air resistance is negligible. Of course, when I throw the object up there, it will lose kinetic energy. And it is used to cover the change in GPE. By the way, this question is too straightforward for 2023, okay? I mean, I don't know, or maybe they just want to give you a bonus. Who knows? Who knows? Cambridge is very, very sus. All right, anyway, you want to find the speed, there'll be 2 change in potential. So in this case, the change in potential is 4.19 times 10 to the power of 7. Whenever change in potential is given, or the potential graph is given, your life is significantly easier already because you don't have to go through the GMM over, you don't have to go through this equation. Only use this if the change in potential or the potential against distance graph is not given, not known. If you don't know this, then sure, you need to calculate. But if you do, you don't need to. All right, anyway, this is 9154, 9150. All right, so the whole calculation part is 5 marks. So practice a bit more if you need to, but the whole point here is if you need to do a long form calculation to find potential, then later on, you shouldn't be using the equation again. You can use the connecting bridges because GPE is also, or potential is GPE per unit mass. So change in potential is change in GPE per unit mass. So you can use this, especially if you already know the change in potential. It will save you quite a lot of time. So the follow-up would be to then provide you, I mean, I'm pretty sure I've recommended some of these questions already, but for questions that look like this, that require you to find the change in potential, you can check out Feb March 17 P42 question 1. This is page 16 in the topicals. And if you want a graph, summer 10, P42 question 1. So this one with the graph. And this one. So you can see the progression of the question through the years. You can obviously start with the earliest one, May, June 10. Up to you lah. You can start with the later one. It's fine. All right, I think these 2 should be enough. All of these should be enough. And then the more recent one would be the ON20 P42 question 1. So questions that are sort of related to this one are all of this. Okay. All right, moving on. So just why the equation is not appropriate? Well, I think if you've joined us for a while, you will know that you want to use the equation, you got to make sure that the gravitational acceleration is constant. So in this case, A is not constant. A isn't constant. And the reason why A isn't constant is because the gravitational force or the gravitational field decreases with distance from the Earth center. Close to the Earth center, then sure, the gravitational field is constant. So within a few kilometers from the Earth's surface, then G is 9.81. But then after that, it's no longer 9.8. Okay, moving on to another one. So this is a pretty similar question. This one is identical, almost identical to the Feb March 17 paper, this one. Okay, almost identical. Okay, so gravitational field, this one is 2007, summer 2007. Okay, so state what is meant by gravitational field. So in this case, if you want to see what gravitational field is, this one is a region of space where a mass experience a force. Okay. All right. So mention that there is mass, the condition that is experiencing a force. All right. So here you have an object, and then we launch it from the surface of the planet so that it move radially. Move radially means move along this line, because this line is along the radius. Okay. So you launch it from the surface of the planet such that the rocket moves radially away. The rocket engine is stopped when the rocket is at a height r. So from here to here, there is engine running. I don't know how much energy the engine is added into the rocket. But I know at the distance r, we turn off the engine. Off. Okay. And of course, the rocket will continue to move, at least for a certain distance. So the mass of the rocket after the engines have been stopped is m. Burn all the petrol already, or the fuel. Rocket don't use petrol. Mostly the fuel is hydrogen or nuclear. Show that for the rocket to travel from r to 2r above the planet's surface, the change in potential energy is given by this expression. Okay, again, first step, if I want to find change in potential energy, I got to figure out where's the starting and where's the ending position. So from a height r to a height 2r. This is initial, this is final. So to find the change in potential energy, I will take the potential energy at the final position minus the potential energy at the initial position. But also at the same time, I need to know what's the equation for potential energy, negative G_mm over distance r. So most of the time, in case I make a mistake, I always write the equation at the side to get the first mark. All right, the final position, we will be at 2r. The initial position, we will be at r. If you're thinking that, then no law. Remember, we always must measure distance from the center of the planet. So actually, the final position is not 2r, it is 3r. And the initial position is not r, it is 2r. Okay, so don't forget to add the radius of the Earth to measure from the center. Okay, this will be negative G_mm. This is negative G_mm. Okay, let me take out the G_mm. What is left here is negative 1 over 3r plus 1 over 2r. Can I factorize the r? Can take out the r, right? So I have G_mm over r. And then what is inside here? Positive half minus 1/3, which is actually 1 over 6. Because half is 3 over 6 and 1/3 is 2 over 6. Or press calculator. So you get G_mm over r times 1 over 6, which is G_mm over 6r. Okay, so candidates being able to write down this equation is worth 1 mark already, most of the time. But I look at the more recent formula page. I'm not sure lah. Let me check first. I look at the more recent formula page or the more recent past year questions. It looks like they are now giving you this equation. Let me check. Yes. So in the 2022 formula page onwards, this equation is given. I mean, not that it should concern you that much. It's given to you already, meaning in 2022, marks will not be given here. But what I hope the mark will go is the students being able to substitute one of this radius correctly and the other one of this radius correctly and bringing it together. Okay, the more equation they give you, the lesser mark you can get. So I prefer if they give you less equations, but oh well. Okay, next. During the ascent, okay, ascent means up, going up. Ascent is going up. Descent means coming down. I think in the recent years, the Angmos, the white people, they know that we can't, if you want to test whether people understand physics, you cannot use fancy English. Let me make sure I spell it correctly. Ascent is going up. So just descent. Descent is down. Anyway, it's going to move from R to 2R. And the speed of the rocket changes this much. So in SI units, the change in kinetic energy is given by this expression. This is way too easy to expect this from 2023. But we're going to take half mv square, or rather the final velocity minus the initial velocity. Okay, so I can factorize the half m. M here is the mass of the rocket. Okay, so the v square that we have, I just want to change lah. So if I'm not feeling it, I can always take the larger minus the smaller one. But since I'm taking final minus initial and I know my rocket will slow down, this is what I'll do. I expect a negative number because I expect the rocket to slow down as it travels away from the planet. Okay, so this would be negative 2.088, 2.09 times 10 to the power of 6 m. So this negative here shows a decrease in kinetic energy. So hence, change in EK, the magnitude of the change in EK will be 2.09 times 10 to the power of 6 meter. Okay, part C, the planet has this radius. Use the expression in B. In B, I got two expressions. I have this GMM over 6R, and I also have this change in KE. To determine the value of M of the planet, well, at the end of the day, we are still using the change in GPE is equal to the magnitude of the change in KE. Okay, so change in KE is 2.09 times 10 to the power of 6 multiplied by M. The change in GPE just now was GMM over 6R. So it's okay to just take the magnitude. We already know which one increase and which one decrease. Okay, so we can cancel the mass of the rocket. And now you can find the mass of the planet by rearranging. So this would be 6 times the radius times 10 to the power of 6 times 2.09 times 10 to the power of 6 divided by, this is a chunky planet, 6.67 times 10 to the power of negative 11. Chapter, because of the prefixes and us dealing with very big numbers, the calculation tends to be, tends to take a little bit more time and care, thanks to all the prefixes just hiding. So 6.392 times 10 to the power of 23 kg. Okay, a heads up, all of this is 3SF. So this one should be 3SF. Sometimes if they give you data in 2SF, then your final answer can be 2SF. Is this one 3 or 2? Like this one all 2SF, right? So your final answer you can leave as 2SF. But this question, all the data is 3SF. 2.09, 3.40. So your final answer should also be 3SF. Okay. State one assumption made in one. Well, I'm going to assume that there is no other gravitational field from other planetary objects. No other planetary objects or stars influencing or the gravitational field of the planet. All right. So hope that makes sense. Whenever you measure distance, they like to do this all the time. They will cheat your feelings by giving you extra distance. Remember that this distance is always measured from the center of mass. In this case, it will be the center of the planet. It may not be Earth, but it is a planet. Later they put Mars. Okay. All right, so that's the question from the Q&A section. It is a same type of question, so I'm not going to suggest anymore. It's the same type, which is these. If you can do this four, you understand they're all about the same. Okay, just a heads up about the significant figures. Sometimes they will increase one and put it to 3, and then make sure you know that the distance are measured from the center of the planet. Okay, we're going to carry on to look at chapter, I guess, the summary for this thing. Okay, so I think I'll rewrite everything for you. Okay, so you can treat this as like a recap. Not everything, but the important equations. Okay, so far in the previous class, we looked at the kinetic theory. The kinetic theory of gases, which is your chapter 15. Okay, so when it comes to kinetic theory of gases, what we're trying to do is we're trying to establish a connection between pressure, volume, temperature, and mean square speed, root mean square speed, mean KE of your gas particles. So you have the macroscopic PVT on the left and the microscopic mean square speed and kinetic energy on the right. All right. So using kinetic theory and particle in the box, we can build that bridge here. Okay. So you should know the assumptions of kinetic theory. And the particle in the box method. We are able to build or to write down the equation P is equal to 1/3 Nm over V C squared. Okay. And this equation together with PV is nRT. So I'm just going to write one here. There's a PV equal to nRT here. There's also a PV is equal to nKT here. So this one plus PV is equal to nKT will give us the relationship between temperature and kinetic energy. Okay. So the derivation I've shown you last time, you also sort of need to know. If you don't know, then it's a bit pain. So this mean KE will be 3/2 NKT for the gas sample. But so this is the total KE. And then the average KE for one molecule or one particle is 3/2 KT. Okay. So you should know how to derive this equation and this equation from the combination of these two. Okay. Then at the same time, based on the equation of kinetic energy is equal to half mean square speed. You can tie to this one, okay? Because your mean square speed is equal to 3 kT over m, where this m is the mass of one particle. One particle or one molecule. Okay lah, these are all your important equations. This is one. There is this one. Then there is also, I guess for me in my brain, it's the same thing lah. If it's one particle, I just don't multiply by n. No? N particles, then I multiply by n. No? And of course, goes without saying, you need to know this lah. Okay. So sometimes they will ask questions just a standalone, but most of the time they will combine this idea with the idea from chapter 16. And chapter 16 is about conservation of energy or the laws of thermodynamics. There's actually, I think, 4 laws, but we only learn one now, okay? So the first law of thermodynamics, which is actually how we understand conservation of energy. So if I look at my my table list here, the energy is kinetic energy because we assume that this is the kinetic theory of ideal gas. Okay, so we're going to make a few assumptions first, or I will remind you of a few assumptions. For particles or for matter, particles, molecules, my chemistry brain, my physics brain are fighting. Okay, so the particles has 2 forms of kinetic energy. And normally, we just assume that they have this thing called internal energy. Internal energy normally will give them the symbol U. Okay, but what does this internal energy consist of? Internal energy is the sum of the kinetic energy of the particles. Kind of makes sense, right? Particles will move, they'll vibrate. Obviously, they have kinetic energy. And potential energy of the particles. So this kinetic energy is tied to the movement or the vibration, if you're talking about solid, of the particles. And this potential energy is tied to the bonds or intermolecular forces. Your covalent bond, van der Waals bond, ionic bond, all the bonds are all potential energy. Okay, so if I want to define internal energy, this is a definition, but I also need to remind you that these values that we have, the kinetic energy and the potential energy, is different depending on where your particle is. So let's say, for example, I have a big block of ice, this particle and this particle and this particle, they will all have slightly different kinetic energy because the movement is random. It will also have slightly different bonds because if you're closer to the surface, my bonds are less. But if I'm, right in the center, I have a lot of bonds. Okay, which means when I want to define internal energy, it is defined as the sum of the random distributions of kinetic energy and potential energy of the particles. So make sure to mention the term random. Okay, it's a distribution. So if you do chemistry, you probably have seen the Maxwell-Boltzmann curve before when you heat up the gas. Can I show? Okay, this is the Maxwell-Boltzmann curve. Ta-da! So if the gas is cold or the particle is cold, I have a lot of particles moving at low speed. But this distribution is random. Of course, I will have particles moving at high speed, but not that many. But if I heat up the particle, the mode of my distribution will shift to the right, meaning I will have more particles at higher speed. Doesn't mean I don't have particles at slow speed. I still have, just less. Okay, So this is the Maxwell-Boltzmann curve. Or logic law, if I heat up my particles, everybody's kinetic energy will increase more. So the average KE will shift. That's why we use the term random distribution, because it's not like all the particles have the same kinetic energy and potential energy. It is a distribution. Okay, all right. So this is number one. Number two, for ideal gas, there is no intermolecular forces. To be honest, all gases got intermolecular forces because of your van der Waals, meaning the orbital electron surely will have some electric field interaction with the orbital electron of another particle. But we are going to assume there is no, okay? Meaning the potential energy is zero, meaning the internal energy, U, is equal to KE alone. But also from chapter 15, or like I've shown you just now, kinetic energy can be calculated using the equation 3/2 nkt. So then the internal energy can be 3/2 nkt for ideal gas, or the important thing is it is proportional to temperature, which means when temperature increases, internal energy increases, assuming the potential energy is zero. Okay, which brings us to the third statement, or rather the third idea to think about when it comes to internal energy. Okay, let's say I have a sample of gas. And I think to myself, ideal gas, sample of ideal gas. I want the gas to have more internal energy. Meaning, I want to increase the internal energy of my gas particles here. What are my options? You could say, well, teacher, it's very easy. If I want to increase internal energy, I should heat up the gas. I should add energy into the gas. So I'm going to add heat plus Q. But let's say I don't have a temperature source, so I can't add heat. Another way that I can change the internal energy is to compress the gas. So maybe I'll replace this with a piston. So I could move my piston lower. Okay, so to increase internal energy, I can also decrease the volume or compress the gas. So to increase the internal energy of the particles, I have two choices. I either add heat and or do work on the gas, aka compress gas. So if I put this together, I can say that the change in my internal energy is actually equal to the amount of heat added plus the work done by the gas. So you think about the gas particle. I want them to move faster. I got two choices. I either add heat, so I can directly supercharge the kinetic energy, so that I can directly supercharge the internal energy, and I can compress the gas. If there's less space for the gas to move, the gas will move faster. Okay, you can kind of make sense, right? When you compress the gas, it will become hotter. Think about your pressure cooker. Okay, so this by itself, from conservation of energy, is the first law of thermodynamics. So if you watch the long lecture series, I will go through them case by case, but the main idea that you need to apply here is, given a sample, and I want the particles to move faster or have more internal energy, assuming it's ideal gas. Ideal gas. I have two methods. I either increase the heat, add heat to the system, and or compress the gas. I can also choose to compress the gas without adding the heat, okay? Which means if, let's say, you were to decrease, it could be due to heat removed or gas expand. This works also. So you decrease in internal energy is equal to heat removed. And for the chemistry people, removing heat is exothermic because you are releasing heat. Okay, anyway, that one doesn't matter. We won't use that term in physics. This is work done by the gas. The gas do the work very tired, so it's work done by gas expands. Of course, the positive version one is easier on the brain, but whenever you do this, think of the sign convention. Okay, so I'll summarize the sign convention here for you. You have positive sign or negative sign. We have U, Q, and W. For U, it's very straightforward. Did the temperature increase? If the temperature increase, then U increase, then the change in U is positive. So I'm going to put delta here. Okay. For negative, temperature decrease, U decrease, change in U becomes negative. Okay. Q is, I guess, self-explanatory. One would be heat added. One would be heat removed from the system. Okay. And the W, whenever you use the equation, try to follow the sign convention. Okay. The W here, if it's positive, means I'm adding energy to the system. So this means the gas is compressed. Volume decrease. Whereas for this one, gas expands, volume increase. So there are macroscopic tells on the signs. If you see temperature increasing, your delta U is positive. If you see volume decreasing, your W is negative. You are expected to know these tells, okay? And the term that we use when volume decrease is work done. If something presses on you, something is doing work on you. So it's work done on the gas. This one is work done by the gas. Think of the Dragon Ball Z. Okay, I don't know, I'm talking to what generation these days? If the Dragon Ball want to shoot the fireball, he will compress the fireball first. So when you compress something, you're pushing all the energy together. Work done on compress the gas. Okay. All right, we'll try some questions here, but I will probably also list down the question type for you. The first type would be graph and tables, the calculation type. The second type would be just pure calculation. And PV equal nRT stuff. Or calculation and Q is MC delta T stuff. Okay. And finally, number 3, we would also need to talk about some explanation using the first law of thermodynamics. By the way, just a reminder from your AS, this work done W is P delta V, change in volume. Can they ask you to calculate? Yes, of course. If you want to know the derivation of the equation, you can check out AS chapter 6. All right. So today we're going to practice questions involving the first law. All right. Conservation of energy. We're going to look at graphs. We're going to look at it combining with other equations. And also we're going to look at how to explain. But at the end of the day, it's all about what we're going to do to increase the internal energy of the particle. Okay. Whether it's to add heat or do work. Okay. So I'm going to print this out again into your passport. And then we will jump straight to do questions. This is for people who may want to look at it if they haven't been copying. Okay, we're gonna do what? We're gonna try by fire. Let's start with the recent questions. By the way, I did not recap much of this because I assume people are okay. But if you need to, let me know, okay? There is the chapter 14 stuff. Q is MC delta T. So do you know how to define specific heat capacity? And then also you have Q is equal to ML. And this L is your specific latent heat. Okay, still important. We'll do the question now and you'll see what I mean. Okay, we're going to start by looking at the one that's fairly recent from Winter 22 P42. If you need, you haven't printed it out, you want to stare at it, I've sent a copy into chat. This is especially for those who are writing, because I don't know. Are you writing digitally? Are you writing physical, hard copy? Okay, you adjust yourself. If you have any special requests, let me know. I will try my best to see if I can comply. If you want me to send the note somewhere, go. All right. First, define specific heat capacity. So I want to do this one because I want to remind people that the definition has changed. Or rather, we need to look at a more recent definition. And because of the sizing, did I bring my iPad? I didn't bring my iPad. Okay, never mind. Specific heat capacity C generally is defined by the equation Q is equal to MC delta T or delta theta. Okay. And when I define this, I mean, I rely on the equation to help me remember. So looks like C is equal to Q per unit mass per unit change in temperature. So I will say that this is thermal energy, which is Q, per unit mass per unit change in temperature. So the older definition, which is the thermal energy required to increase 1 kg by 1 degree Celsius, we will replace them to increase 1 kg per unit mass by 1 degree Celsius per unit change in temperature. Okay, this is the recommendation of the recent mark scheme. All right, B. A fixed mass of water in a beaker is at atmospheric pressure. The initial temperature is 0 degrees Celsius. The water is supplied with thermal energy E. Okay, sure, not Q, but E. Fine. So that the temperature increases to 8 degrees Celsius. So this is my delta T. There is no net change in the volume of the water. All right, so every sentence is kind of like a clue. No net change in the volume of the water because W is pressure times change in volume. So no change in volume, W is equal to 0. Use first law of thermodynamics to complete the table for this process. Wow, work done on water, 0. Okay, 0. Right? The thermal energy supplied to the water is plus E. And then, teacher, how do I know what's the increase in internal energy? Think of the first law of thermodynamics. Delta U is equal to Q plus W. But Q is the thermal energy supplied to the water, which is E, positive E, and your W is a big fat zero because there's no change in volume. So delta U is actually equal to also positive E. Nice, right? I like questions like this. Okay, everything is in the question already. If you know how to use the sign convention. Is it important to write the positive? Not really, but I tend to do it just to double check. Okay, especially if there's a negative sign, that I forget to write. Okay, so writing a positive sign forces me to think about whether there should be a negative sign there. But it's up to you. Please write E at least. Okay, number 2, the water is now heated so that the temperature is increased by a further 8 to a final temperature of 16 degrees. So plus 8 plus 8. This process causes the volume of the water to increase. Ooh, interesting. So if I heat up the water some more, V increase, volume increase. Okay, so that work is done. Assume that the change in internal energy is the same as B1. Use the first law of thermodynamics to complete the table of 2.2 for this process. Okay, so they say W is work done, W is done. So this one has to be W, but because volume increased, so it is negative W. Is a negative important? Oh yes, a negative is compulsory. If there's a positive there, you didn't write a positive, you won't lose mark. It's a negative there, you didn't write a negative, confirm will lose mark. So this one is because the volume decrease. Right? So we need a negative there. It says that assume the change in internal energy is the same. So I guess this is still positive E. Internal energy is the same as B1. Okay, so if I'm going to use the first law of thermodynamics, change in internal energy is Q plus W. But my change in internal energy now is positive E. And I'm looking for Q because I don't know what to fill in here. This is Q. This is delta U. And this is W. And W is negative. So Q will be equal to E plus W. The thermal energy supplied to the water is E plus W. All right, moving on. Use the information in B to suggest with a reason how the average heat capacity between 8 and 16 compares with the average value between 0 and 8. Okay, so at the end of the day, the thermal energy Q is equal to mc delta theta or delta T. Okay, so between 0 degrees Celsius to 8 degrees Celsius, Q is equal to E. So mc delta T is equal to E. C will be equal to E divided by m delta T. Okay, repeat again. For 8 degrees Celsius to 16 degrees Celsius. Right now, your Q would be E plus W. I need more energy to expand. Okay, which means now C would be E plus W over m delta T. So obviously, the specific heat capacity between 8 degrees Celsius to 16 degrees Celsius is greater because more thermal energy is required. since there is work done by the water during expansion. But the key phrases here is because you need to mention that the thermal energy required is more. This is the key phrase that we're looking for, including the specific heat capacity is greater. Do you need to do the maths that I've done this expression that I've done just now? Not really. If you can actually visualize the fact that now the objective of adding heat is to increase the temperature by 8 degrees Celsius. The first 8 degrees Celsius, I don't need to expand. The second 8 degrees Celsius, I need to expand. So when I need to expand, I here being gas, I need to eat up more heat for that expansion because the change in temperature is the same. Okay, so there's added work done by the water, which means I need added energy, which means I have a larger specific heat capacity. That is the entirety of the question. I think it's pretty okay. Don't get too freaked out if if they ask you in a format that you've never seen before. It's okay. Doable. Okay, so speaking of which, I'm gonna move on to do the other variant. Okay, so this one is very nice. Look at these 3 marks. If you write down the meaning of each symbols, okay, so we pray we get this question. Okay, I don't know what's gonna come out, okay. But for this one, they are asking you to state the equation, state the meaning of each symbol. So P would be pressure. V is the volume of the gas, I guess. The gas. N is the number of particles. Or number of molecules. K is the Boltzmann constant. You can also copy from the formula sheet if you don't know how to spell his name. And T is thermodynamic temperature. Send the image in. Thermodynamic temperature. Of the gas. So please remember to mention thermodynamic temperature to show that the temperature is in Kelvin. Okay, so this is 1 mark. Number of particles or number of molecule is 1 mark. And then finally, the other things are 1 mark. This one. Okay, nice and easy. Moving on. Use the equation in A to show that the average translational kinetic energy is this. So as mentioned before, they can ask you this, and we wanted to start with PV is equal to NKT, but also at the same time, you can flip to your formula page and use this equation. P is equal to 1/3 NM over VC squared. So I can rearrange PV is equal to 1/3 NM C squared. Equation 1, equation 2. So 1 is equal to 2. NKT is equal to 1/3 NM C squared. The N and N should go away. And then here I will have 3KT is equal to MC squared. Multiply both sides by half. So 3/2KT will be half mass times speed squared, which is kinetic energy. Proven. Okay. So if you write down this equation and you equate them, you get the first mark. And the second mark is just the algebra. If the lecturer or the person marking understand your algebra, you are good to go. So most of the time, I will insist students at least write this formula. Okay. All right, the mass of an oxygen molecule is this much. Assume that oxygen behaves as an ideal gas. My polar bonds disagree, but never mind. Okay, use the equation in B. Okay, if it's not ideal, we cannot use the equation. So we want to use the equation. To determine the root mean square speed of an oxygen molecule at 23 degrees Celsius. Okay, so the equation in B is this. Kinetic energy is 3 over 2 kT. Okay, so in this case, if I want to find the mean square speed, this is half mc square is 3 over 2 kT. So I can find c square. This is 3 kT over m. So root mean square speed is equal to the square root of this, which will be the square root of this whole thing, Boltzmann constant. I can put my values in already. Negative 23. The temperature is 23 degrees Celsius. We should not forget to add 273 to that, divided by the mass, which will be 5.31 times 10 to the power of negative 26. So when you do questions like this, sometimes they may not give you the mass of the molecule. They may give you the mass of the sample. Then you need to use molar mass to find. Okay, so I've made a note here. If let's say, for example, the mass of the sample is 16 gram, okay, which is the molar mass, then the mass of one particle, this is equivalent to 1 mole of oxygen. Is it? Doubt myself. Don't have periodic table. Hang on. Oxygen is 8, 16 are correct. It is 1 mole of oxygen. So mass of one particle will be 16 times 10 to the power of negative 3 kg divided by how many particles are there in 1 mole? 6.02 times 10 to the power of 23. This is what I mean by if they never give you the mass of one particle, they should at least give you the molar mass or the mass of 1 mole or the mass of 2 moles or whatever corresponding mass that they can give you. Then if you divide them, you will get the mass of one particle. Okay. Obviously, it's not the same as this one because I'm not quite sure. Oh, not quite sure whether they're talking about O or O2, but I will stick with this value. Okay. Anyway, if I press the calculator for this, should be able to get 480. 2SF because 23 degrees Celsius is 2SF. That's 1.38. Negative 23 times 6. So 480.4. If you didn't square root, right, you get something very ridiculous. That should be a sign to you that something is off. Okay, because if you didn't square root, it will be 2.3 times 10 to the power of 5. This is way too fast for gas. Gas normally, okay, this mean square speed, this CRMS is normally between few hundred to 1,000. If you have anything that is more than 1,000, unless it's a hydrogen, it's very weird. Sus. What more if it's 5 figure? Okay, so few hundred meter per second to 100 meter per second, 1,000 meter per second. So if you don't get within the range, either you use the wrong mass or you forgot the square root. So cannot be too slow, it cannot be too fast. 100 plus to 1,000 is okay. All right, moving on to the next part. Looks like an interesting diagram here. A fixed mass of oxygen at the initial pressure P is sealed in a cylinder container by a movable piston at one end. The temperature of the gas is 23 degrees Celsius. Piston is slowly moved into the cylinder. So we're gonna move the piston into the cylinder like so that the oxygen gas is compressed. Oh, interesting. So if the gas is compressed, this is positive W. At all times, the gas and the container remains in thermal equilibrium with the surrounding. What does this tell me? If it remains in thermal equilibrium, means it has the same temperature as the surroundings. So if it's the same temperature as the surroundings, does the temperature change? No, no, temperature is constant. Okay. On figure 3.2, sketch the variation with pressure, the RMS speed of oxygen as the pressure increases. Okay. Of course, you could be asking me, teacher, is it possible? How is it possible when I compress the gas and the temperature doesn't change? Can. Boyle's law. Your P1 V1 equal to P2 V2. I just need to do the process very, very slowly. Slowly. Yeah, slowly. So if I do it very slowly, then whatever extra energy it has, it will be, sent out as heat, meaning it doesn't register as an increase in temperature. Okay, all you can see here, thermal equilibrium means same temperature as surrounding, temperature is constant. Oh, what is U? Did I tell you what is U? U? Is U the value we calculated? Ah, yes. This is U. Root mean square speed. Yeah, teacher, internal energy, they use U. Root mean square speed, they use U. Yeah lah, to confuse you. Don't be confused. No matter what symbol they use, they have to define it for U. So if the root mean square speed is U, that means the temperature is constant and the speed will be constant. Like that. Huh? Like that 2 mark? Yeah. Just hashtag troll. Anyway, temperature is constant. So the root mean square speed, or in this case, U, which is so a bit of a confusion, but U is 3, what was it again? Copy here. 3 kT over m square root. 3 kT over m square root. So temperature constant, meaning this U is constant. Because obviously the mass of a hydrogen molecule is not going to change, which means the mass of, the Boltzmann constant is not going to change. So everything in front here, these are all constants. So when T increase, U will increase. Or logic lah. Temperature stay the same, the particles will travel at the same speed. Okay. So don't be too afraid when they are asking you to sketch something, although you haven't seen before. We've done this a lot in your AS, you gotta trust yourself. But also at the same time, the question should give you enough information. So take some time to read through the question. All right. Okay, we're gonna now jump and do, let me take a peek at the FedMarch 2-3 paper. Are they? Okay lah, I won't touch the May June 2-3, mainly because I don't have them. But also, at least I don't have the full variants. I want you to keep it for when you feel that you are ready to try the whole paper. The whole paper is quite long. But I can look at the March 23 papers. Yeah lah. Nothing special. It's a very standard past year question, not worth discussing. So you keep that question for later when you feel that you're ready. Okay, so now we are past the 1 hour mark, so I'll take a break. But when we come back, I will focus on doing the graphs, the cycle graphs, and also the explanation. Okay. In the meantime, you can check out the questions that I've selected. They're also in your Google Drive. Yeah. Okay. And if you have any requests or any questions, you can let me know. But I think I'll start off by looking at page 46 and 47. Yeah. Something with this one. Okay, so I'm going to set a clock for 10 minutes. I will jump straight back into class after that. I'm going to resume recording. Okay, so this question is a little bit anomalous. Maybe I'll do a normal question first. Then I explain to you why I think it's anomalous. Okay, a normal question is like this one from summer 22 P41. And I think I'll print it out separately so that it doesn't look very small. Check. All right, this is page 47. If you are using the topicals, which you should. Okay, so this question starts off very light. It's starting by asking us to define what is meant by ideal gas. So ideal gas is generally any and all equation that obeys the relationship PV is equal to nRT, or more specifically, PV over T is equal to nR, which in this case, or in all cases, unless there's a leaking in the gas, that it is constant. Okay, so we define ideal gas by gas that obeys the relationship of PV over T is equal to a constant. All right. So a lot of the definition in this particular subtopic is relying on the equation one, which is always nice. Okay. Or if you don't want to write PV over T is constant, you can say relationship of PV is proportional to T. But since we write down these symbols, we should also define them. So where P is the pressure, V is the volume, and T is the temperature of gas. So one mark is when you mention that it obeys the relationship. The other mark is when you define the symbols that you use. Please define the symbols that you use for a chapter, especially for this topic lah. Okay, they continuously ask students to define PV and T, which, speaking of which, a core memory is to write this as thermodynamic temperature. All right, calculate the amount of gas. This one can easily be used. It can be done using PV is equal to nRT. N would be P, which is 1.2 times 10 to the power of 5, V 0.24, R is 8.31, temperature is 17 degrees Celsius, which we should remember to change it to Kelvin, thermodynamic temperature. This would show us that this is 12 moles of gas. Okay, so if they're asking you the equation of states or basic PV equal to nRT questions, you should be able to do them fairly easily. Okay, just be mindful about the units, especially reminding people that this is thermodynamic temperature, not just any temperature. Right. There is an older question regarding this equation of states where you are required to sort of find out how much gas is leaking. I think it's also in the official example list. But as a note, I should probably state it here if I can find it. Yes. So the more harder equation of state question is this two. You can find them in page 2 of the handout. Okay, this one are all regarding using this equation. Or PV is equal to NKT, depending on the question. All right. So it says here that the gas is going to go through 3 successive changes labeled for you. This is like what I like to call a cycle graph. When I see a cycle graph, the first thing I do is I check the axis. Okay, I have to make sure it is PV and not V against P, because the shape will look very similar. What happens if the graph is V against P? Well, you try them and you tell me. I think the only difference is the work done. We'll talk about that later, but I'll write down the question number. Okay, this is when the axis is flipped. So I check the axis, make sure I circle any prefix or non-SI units to use later. But we are going to go from A to B, B to C, and C back to A. Okay, and I have to read this carefully, especially whenever they talk about energy transfer. So the initial state is A, and the gas is cooled at constant pressure to B by the removal of this much thermal energy. Meaning from A to B, here to here, I will have negative Q, or I lose 48.0 kilojoule of heat. Okay, gas is then heated at constant volume to point C. So obviously this one is plus Q. I don't know plus how much, but it's plus. Okay, heated. Finally, the gas expands at constant temperature back to its original pressure and volume. During this expansion, the gas does a work of 31.6 kilojoule. Okay, so a brief reminder about this kind of work done, especially when expressed in the PV graph. Okay, work done, although I told you is P delta V, the actual version of it is actually integration P dV. In other words, it is the area under the PV graph. So if I have a graph of P against V, let's say it changes this way, this would be my work done. Positive or negative depending on whether the gas expands or is compressed. This is my work done. But teacher, what happens if we flip the axis? Well, if you flip the axis, your graph will still look the same because P and V has that kind of relationship. Okay. But then your work done would be here because of the dV. So if you do calculus, you know what I'm talking about. If not, then remember it is with the V axis. Okay, so this one is now your W. All right, but in this case, they told me already the work done from C to A is 31.6. Okay. All right. With all that information, I probably need to fill it in here. They already fill in the 48 and 31.6 for me, which is nice. But in part 1, you're asked to show the magnitude of work done during AB is 19.2 kilojoule. Okay, so if I look at the process from A to B, which is here to here, I basically need to find the area under the graph. This is my area. Because this is my work done. This is the V-axis. Okay, so the pressure that I'm working with, this is 1.2. So work done is P delta V. Okay, the pressure will be 1.2 times 10 to the power of 5. There's a 10 to the power of 5 at the axis. Okay, the change in volume would be 0.24 change to 0.08. 0.24, 0.08. Two, 0.24, 0.08. So this one would be 1.92 times 10 to the power of 4 joule. Let me yoink this back to the initial position. Okay, which is approximately 19.2 kilojoule, or equal to 19.2 kilojoule. All right, so now we are supposed to complete the table. So to make my life a bit easier, I'm going to move the table so that it's right beside the graph. So bear with me for a bit. Let's crop all the things. All right. So the first thing I want to think about is, where do I put the 19.2 kilojoule? Okay. So put in the information that I have. We know that 19.2 is the process from A to B, and it is under work done. So from A to B, your volume is decreasing, right? So if the volume is decreasing, then work done is positive. So this would be positive 19.2. No need to write kilojoule. Kilojoule is already in the title. Okay, so that means from A to B, the area under here is positive. If you want to, you can write that this one shows that the gas is compressed or volume decrease. Okay. All right, what else do we know? I know there are places where work done is 0, B and C. Why? Because volume constant. And this 31.6 kilojoule of work is from C to A. And C to A, you get a negative here because volume increase. Okay, so a sign will check out one. They don't always have to write for you. They're being nice now, they put it there for you. You should still also be able to transfer from the information into the table yourself. All right, so what else do we know? We can link the graph horizontally. I like to call this Sudoku because this is W, this is Q, this is delta U. So delta U is Q plus W. So to find this delta U, I will take 19.2 plus negative 48.0. Do I need to show working in the exam? No, you don't. I show working for you only. So this will be negative 28.8. Okay, don't worry about the kilojoule. They're all in the table, in the header of the table. Okay, what else do we know? I feel like I need to fill in one more other thing. And I want to point out here that there is constant temperature. So when reading this kind of thing, whenever there's a constant something, there is always information to include one. So if temperature is constant, if you remember the question that we did before the break, constant temperature means same U, same internal energy. So the change in internal energy is 0. 0. Why 0? Because the temperature at B is the same as the temperature at C. Okay, which means this is a closed cycle. So when I sum the change in internal energy, it should be equal to 0. Maybe this is not a good sign. Sum of the change in the internal energy is 0 because why? The initial conditions is equal to the final conditions. So meaning you have the initial, you start with A and you end with A, same pressure, same volume, same temperature. So the sum of the change in your internal energy will be 0. So that means negative 28.8 plus 0 plus the change in internal energy from C to A will be equal to 0. This means the change in internal energy from C to A is 28.8. Does it always, is always one of them 0? No. But in this case, one of them is 0 because the temperature is constant. Okay. Okay, sorry. C to A is the one that's constant. My bad. Is it? C to A. Yes. Hang on. Okay, this makes more sense. Wait, I need to swaps. Need to do a swap. This one will go here. This one will go here. It is TC is equal to TA. Gas expands back to its original pressure to point A. So TA equal to TC. Okay, so I change this to BC. You need to write the working? Nope. Just need to practice. Everything here, but it's also okay to take your time and write them down. The sum of this column have to be 0. Sum is 0. If the cycle is closed. They have never asked for open cycle before. Also, it's very weird to have an open cycle. All right. Anyway, now I can just continue to horizontally fill them in. Okay. So if I want to find Q, Q will be delta U minus 0. So this would be negative 28.8. And then if I want to find this Q would be positive 31.6. This table is worth 5 marks. So if it comes out, it's always a nice thing. The best. Yep. So flip through the topicals, find questions like this. If you are lucky and you see them and they're not problematic, which they can't be unless they change the table, which we will do next. Okay, so this is a very standard question. You can find quite a few of them by just flipping through the past years. Okay, so it's about you looking at the graph and the information given and then deducing the right places. Okay, I know this one is weird because this one is 0. So this one can't be 0, right? 0 all the way. That means the gas didn't change anything, which is not the case because obviously from B to C, the gas did change something. Okay. Whether this is not negative, this is positive. W plus Q is delta U. Too many things. Okay. This plus this is this. This plus this is this. This plus this is this. Yeah. Because from B to C, heat is added. All right, let's check out the one from Feb-March 22, I think. 22, 23. The one with the weird table. Yep. That'll be page 46. So for many generations, people are used to this table. The graph can flip. So if you want to know which one has the VP graph, I'll list it down here for you. That would be Winter 10 P41 question 2. In my topical, it will be page 7. Just being a bit naughty with you. I think in the recent years, there's also another VP graph. But nah. There's another strange one that you should try. Feb-March 17, P42, question 2. Page 26. Okay. All right, this one. So this graph is a P against V graph. And then if you look at the table, this table is a bit different. Instead of changing internal energy, change internal energy, Q and W, the variables is P, V, and T. Which is very weird, okay? Just weird. But anyway, doesn't matter. You are given the graph and you're given the values. At first, you're asked to state the change in internal energy of a complete cycle. The complete cycle, the change in internal energy is 0. Because we return back to the original state. Right, next, calculate the amount of gas. So obviously we're going to use PV is nRT. And I'm going to use the row where I have all PV and T, right? So P would be 1.5. Don't forget there's a prefix times 10 to the power of 5. V is 4.2 times 10 to the power of -3. We're looking for N. R is 8.31. Temperature is, thank God, already in Kelvin. So you can find N. This chapter, very nice one. -3, 8.31, 5.4. Okay, so this would be 0.14 moles. 2SF, because I look at the data in the table, they're all 2SF. So why not? Okay. So moving on to the next part. Complete the table 2.1. Use the space below for any working. Okay. All right. So I like constant things. For example, I know the pressure for Y is equal to the pressure for X. Same P on the P axis. So if the pressure of X is 1.5, pressure of Y is also 1.5. Okay, not complicated one. Just look at the table only. Okay, what else is constant? Well, the volume. So from here, pressure of X is equal to pressure of Y, which is this value. And then the volume of Y is equal to Z, right? Volume of Y is equal to volume of Z. These two volume must be the same. But it's not 4.2 lah, because 4.2 is here. So what are the other information or the added information here that will help you find either something about the volume, especially the volume from X to Z? So let's look through the question. This one is an ideal gas, right? So it will obey the relationship of PV over T is constant. So I just need to find either Y or Z. Maybe I'll find Y. Maybe I'll just take the process from X to Y. Okay, so Px, Vx over Tx, which all also I have, is Py, Vy over Ty. So the pressure of X is 1.5. In this case, if you don't include prefix, also never mind, because left and right will cancel. But, if you don't feel that safe, then include it. Is Vx divided by Tx is 540. Py is 1.5 times 10 to the power of 5. I'm looking for Vy, and the temperature of Y is 230. So if you're a bit perceptive, when I use from X to Y, pressure is constant. You can immediately cancel out pressure already because Px equal to Py. Or if you substitute, then you cancel here. Okay. So from here, your volume of Y, the volume of Y is 4.2 times 10 to the power of -3 multiplied by 230 over 540. So this would be 1.788888 or 1.8 lah. I stick to 2SF. But Vy is equal to Vx, so this makes this 1.8 as well. So it's not very common that they use the ideal gas equation this way, but they have used it several times in different contexts, just not always with the table and the graph. Because normally when table and graph, they expect internal energy, heat added, and work done. But it's also totally fine if there is none. Okay, so that's all. If you need to show the working, then show the working here. Okay, moving on. The first law of thermodynamics may be represented by this equation. Sure. with reference to the system. The system is the gas system. Explain what is meant by delta U, Q, and W. So when you see a delta here, I need the word change. Change is so important. Change in internal energy. And then because they say to the system, then I must say change in internal energy of the gas system. Paranoid a bit lah. NGL, sometimes when you look at too many mark scheme, you start to develop a paranoia. Okay. But the important thing here, actually, yeah, because this is positive, instead of change, I should put increase, right? Because everything is positive. So my bad. Increase in internal energy. Just like Q would be thermal energy or heat energy added to the system or supplied to the system. And then this W positive, so it's work done on the system. So we don't just need you to tell me how it's interacting with the system. We also need the word increase or added or work done on. Okay, 1 mark for each statement. All right, then explain how the first law of thermodynamics applies to the change from Z to X. Let me look at the graph again. Z to X. When you go from Z to X, you realize your pressure decreases. Or rather, I'll draw the graph here. This is Z to X. This is your PV graph. So whenever you want to explain using first law, write a statement about U, write a statement about Q, and write a statement about W. Okay, so you definitely can tell from Z to X that the temperature has increased. Increase or decrease? Z to X, decrease. Yeah. This Z is 782 Kelvin. This X is 540 Kelvin. Okay, so based on the information here, I can say that the internal energy decreases because temperature decreases. I mean, during Z to X lah. Okay, I can't deduce Q because I can't tell. This one don't know. Remove, added. Okay, I'll comment about that later. What about W? You see a volume decrease, right? Okay, so volume decrease means work done on volume decrease. No, volume increase. So work done by the gas. So you should mention internal energy decreases because temperature decreases. Work is done by the gas since volume increases. So if I think about your delta U is Q plus W, which means Q would be delta U minus W. But, you know, this delta U is negative because internal energy decreases. And this work done by the gas is also negative. So I actually don't know whether heat is added or removed because I don't know whether the change in internal energy is bigger or the work done by the gas is bigger. I don't know which one is bigger. And because I don't know which one is bigger, I cannot conclude. Meaning I don't know whether Q is positive or negative, unable to tell. If the change in internal energy is bigger than W, meaning the drop in internal energy is greater than the work done by the gas, then Q is negative. That means heat is removed from the gas. If delta U is less than W, then Q is positive, heat is added to the gas. So it depends on which number is bigger. So if I explain from first law of thermodynamics, I cannot conclude Q that I don't mention. Furthermore, it's only 2 marks. Okay. But generally speaking, whenever you see first law of thermodynamics, think about one statement about the change in internal energy, which is always related to temperature. One statement about Q, either you read the question, they tell you heat is added or removed, or you have to deduce like this yourself. In this case, we cannot conclude. Some cases we can conclude maybe both of them are negative or both of them are positive, then you can. If one negative, one positive like this, then we don't know. It depends. You don't like answers like this, right? It depends. Okay, anyway, this one W. So think about volume changes. So this is a slightly anomalous question. Just scratch, annoying to some. Okay, what shall we do next? Okay, we should do the other variant from summer 22. Again, if you have requests because you've done certain questions, throw them my way. This is a very anomalous question. They've never asked this before, where you are asked to fill in the temperature and deduce your law this way. Not undoable, just a bit different. Okay, so the next variant is page. I want to do the 2022 variants. So page 48. Which will be the next page if you printed the handout. Let me go. Okay. So this question starts off, and I like this question because it links 14 and 16. Okay, it starts off by asking you to define the specific latent heat of vaporization. So Q is equal to mL, which means L is equal to Q over M. Okay, so when it comes to this kind of definition, pretty important to go back to the equation, as mentioned before. So this will be the thermal energy per unit mass required. Vaporization is when you change state from water, liquid to gas. So if they already mention vaporization, if they just say specific latent heat, then it's just to change the state. But if they mention vaporization, then you should probably also mention that this is a state change required. Thermal energy per unit mass required to change the state from liquid to gas. But also important to mention at constant temperature. Because liquid can change to gas at non-constant temperature, evaporation. So the first mark would be thermal energy per unit mass. It's mentioned many times to you already. Nowadays, during definition, if there is like a divide by M, whether it's gravitational potential of this chapter, think about per unit mass. Okay. The second mark is to change state from liquid to gas and at constant temperature. All right. So in this question, you are given some data about water. The pressure is this much. The specific latent heat of vaporization is this much. This is L. This is P. This is mass of the sample. And this is the temperature. So a mass of 0.37 kilogram of water at 100 degrees Celsius is provided with thermal energy needed to vaporize all the water. So we are boiling everything at atmospheric pressure. Okay, yes, we can use Q equal to ml. Okay, don't have to overthink it, it's only 1 mark. This is 2.3 times 10 to the power of 6 joule per kilogram. So this would be 8.5 or 8.51 times 10 to the power of 5 joule. I'll stick to 2SF lah, since all the values given are 2SF. Right. The mass of 1 mole of water is 18 grams. Okay. Assume that the water vapor can be considered to behave as an ideal gas, so ignore hydrogen bond. Show that the volume of water vapor produced is 0.64 meter cube. So we can use PV as nRT, okay, the ideal gas equation. But I have the pressure. Let's put in the values that we have first. Okay, I'm looking for volume. Do I have the number of moles? It's not 1 molar. I have 0.37 kg. It's n mole. But I know 18 gram is 1 mole. So you know how to find n? N would be 0.37 kg. So I'm going to convert this to gram. So I can divide this by the molar mass 18 gram. Okay, because 0.37 kg is 370 gram. Yeah. 8.31. And the temperature is 100 plus 273 because it's boiling. So if you do this right, this would be 0.64 meter cube. So this is what I mean by, especially if you don't do chemistry, apparently you can in A levels. So if you're not doing chemistry, then bear in mind that you need to know a little bit of basic about mole concept. 1 mole is the same as the molar mass. Okay. Anyway, we're going to continue to part 3. Assume that the initial volume of the liquid water is negligible compared to the volume of the water vapor produced. So that means I have this much steam. Water vapor is steam, right? But compared to the volume of the water when this started is negligible. So determine the magnitude of work done by the water by expanding against the atmosphere. So I can use P delta V. The pressure of atmosphere that I'm pushing again is 1 times 10 to the power of 5. The change in volume is 0.64 minus 0 because the initial volume is negligible. So I put the 0 here. So this would be 6.4 times 10 to the power of 4 joule. Very nice. Very doable. Okay, moving on. Using all your answers that you have calculated just now, determine the increase in internal energy of the water when it vaporizes at 100 degrees Celsius. Explain your reasoning. Okay, so delta U is Q plus W. We calculated the Q just now, right? The Q just now was 8.51 or 8.5 times 10 to the power of 5. And the work done that we calculated just now was 6.4 times 10 to the power of 4. So can I just add them together? No, the 6.4 must have a negative. And, you know, because that's why when I use this, I always, even if it's positive, I'll add the sign there just to double check. Okay, so this negative here is to show that the gas is expanding or the water vapor is expanding. When you boil, the steam expand against atmosphere. Or if you do not think too much, volume increase. So there has to be a negative sign here. This positive here is also very dull because during boiling, heat obviously have to be added. If not, what is boiling if heat is not added? There's a positive sign here. Okay, so from here, the change in your internal energy would be 8.5 minus 0.64, 7.86 times 10 to the power of 5. You could write 7.9 if you're sticking to 2SF. Cool. Part C. Use the first law of thermodynamics to suggest, with a reason, how the specific latent heat of vaporization of water at a pressure greater than atmospheric pressure compares with the value at atmospheric pressure. Okay, basically, I'm going to repeat this process again, but I will increase the surrounding pressure. First step, don't panic. Wow, this question 12 marks. Well, don't panic. Look at the calculation you've done so far. Whenever I want to, okay, maybe I'll write here. Okay, we want to repeat the experiment at a greater pressure. So let's think about your delta U is Q plus W. So this delta U, again, we assume the water vapor is ideal gas. Very weird. But this one is going to be constant because the temperature, the change in internal energy is the same because it's a state change. Okay. But let me adjust this to include pressure. P delta V. But there's a negative here because it's expanding. So I'm gonna put this one here, negative P delta V. Okay. But also at the same time, this Q is equal to ML. I think the first thing I want to address is the W. Greater P, greater W. Okay. So as the water vapor expands at higher pressure, more work is done by the steam, by the gas. They call it steam. Just put by the vapor, by water vapor. Okay. So for the same state change, which by the way, same state change means there's the same change in internal energy. If I want to keep this one constant, if this value becomes a bigger negative number, then this Q have to also become a bigger positive number so that the net change is cancelled out. Okay, so there's the same state change at the same temperature. So there's the same change in internal energy. So delta U is constant. So because of this, more heat is required. It's down a bit. More thermal energy is necessary or needed And because of this, there is a greater specific latent heat. Specific latent heat increases. That's why it's easier to boil water at higher pressure, sorry, higher altitude, because the pressure is lower. If you bring your pot and you want to boil water at Genting Highlands or Mount Everest, then it's easier to boil water there because the pressure is low. But if the pressure is higher, let's say you go into a submarine and you sink into the ocean, you probably need more heat. Okay, so I repeat now. If it helps, put numbers. Let's say this is 100, this is positive 50, this is negative 50. Okay, if pressure increase, then instead of negative 50, maybe this is negative 60. But if I still want this one to be 100, wait, my maths macam not working. Okay, if I want this one have to be 150. Let's say change in internal energy is 100, so it's 150 minus 50. If let's say my work done has increased to negative 60, this one still need to maintain 100. My delta U still have to maintain 100. This means that my heat added has to be 160. Okay, because the negative number is getting bigger, so the positive number also have to get bigger so that the net change is 0. How do I know the net change is 0? It's the same state change. Okay, so the main point here is number 1, you explain how it affects the work done. Higher pressure, more work done, or greater work is done by the water. By is important. I normally just like overload with all the keywords, expand by the water. Okay. So the negative W become more and more negative. If I want to maintain the same change in internal energy, I need more thermal energy. So that's why the specific latent heat increases. All right. So the recent years, the question, they like to like merge and combine either chapter 14, 15, and 16. They like to pick and choose different ideas and put them together, as you can see from the more recent questions that we've been doing. All right. So I think the last thing I want to remind you before I close out this chapter is that at the end of the day, when you think about your delta U is equal to Q plus W, I haven't done much explanation questions because they're not that popular now. But in case you want to practice, there are some in the formula or the formal playlist. I will recommend them to you with the recording later. Okay, so just a reminder here, this delta U has ties to kinetic energy. So it's equal to the sum of random distribution of Ke plus Pe. And specifically for ideal gas, Pe is 0. So delta U is equal to Ke, and delta U will be 3 over 2 NKT for your gas sample. So this one has ties to temperature. If T increase, internal energy increases. If T decrease, internal energy decreases. You know what? I'm just going to put delta T here. Okay. So here itself can tie to mean square speed BRMS as we have done just now. Okay, especially the kinetic energy. So this one goes to chapter 15. Q can be calculated using either MC delta T, as we have done some question just now, where it ties to the change in temperature. So you see there's another change in temperature here. Because its heat is added or removed from the system. We obviously, like the previous question just now, also have Q is equal to ML. So I can merge chapter 14 with this one. Okay. And finally, work done, W is P delta V. So there has to be a change in volume that is tied to W. But hey, do you realize that there is P, there is V, there is T? So above all else, this one, we can also use PV is nRT or PV is equal to NKT. This is for the states, pressure, volume, temperature, but they have ties to the energy equation, which is delta U is Q plus W. So for them, it's like a buffet, you know. Today, maybe they feel like setting a question, focusing on internal energy and then KE and PE. Okay, lor. Tomorrow, they feel like linking specific heat capacity and boiling, specific latent heat and boiling, sorry. And then after that, they may ask you to think about the change in volume and work done, or any combo of all of this. So PV and T can be used to describe gas. So just remember that be flexible between the links across the different topics, okay? So what I did not cover that you should go and make sure you try some questions. The calculation involving this, I already include this in the formal question that I have printed out for you. So I'll just write the page number lah. Page 31 in your topicals, page 19, okay? And then there is also the using this to explain. These questions are very repetitive. So I think Cambridge realized that it's repetitive, so they stopped asking already. But just in the case where they suddenly realize, hey, we haven't been asking for these past 3 years, maybe we should ask again because why not? Then look at this one. This is already recorded, page 25. Okay. So if you've done the key question and you've added this one, this asterisk, and you understand the concept, you're okay already. All right. I will put up questions for chapter 17, oscillation, for next week. So if you can, you should try them before class to identify any help that you may need. And then please ask me questions so that I can address them in the beginning of class or throughout the week if your questions are easy to answer. All right, don't be shy. Okay, thanks for staying back. I'll see you next week. Take care. Stay safe. Stay healthy. Make sure you get enough sleep. Thank you. It's a very quiet online class. Thank you. Bye-bye. Enjoy your dinner. See you. I record.